Hi everyone, I'm Peter Yoachim from the University of Washington and the Rubin Observatory, and I'm here to tell you about using an artificial intelligence to generate a big data set. So my image here is a recent image from the summit where Rubin Observatory is being constructed, and you can see the full moon in the background there. So a very brief introduction to Rubin Observatory, formerly called LSST. We're an 8-meter telescope on Cerro Pachon in Chile. We have a 3.2 gigapixel camera that's seen down here. It's about the size and weight of an SUV. And we're going to be taking 30-second exposures with this camera, generating about 10 million alerts per night. The data is going to go from Chile up to NCSA in Illinois, where every difference image will be computed in 60 seconds, and new alerts will go out identifying new supernovae, new asteroids, anything that's changed image to image. So we're going to be generating about 20 terabytes per night and 15 petabytes after a 10-year survey. So we're planning on taking about 800 observations per clear night. And so the question I'm trying to address is, where exactly should we point the telescope? Because obviously if we take a lot of images, we'll generate a lot of alerts, but we want to maximize the science that we get out of this telescope and camera. Some motivation for our scheduler: we have a science requirements document that says we need to observe an area of 18,000 square degrees 825 times over 10 years. And we need to measure some parallax and proper motion to a given precision and have some rapid revisits. But mainly we have 4 science cases that we want Rubin to address. We want to look at the nature of dark matter and dark energy. We want to make a catalog of the solar system. We want to look at the variable sky. And we want to measure the Milky Way structure and formation. So those are kind of our driving cases. Here's what we would like the final survey to look like. You can see this big yellow region is what we call the wide, fast, deep, or that 18,000 square degrees. And so our goal is to have a scheduler that will give us this survey, and with these different regions. You can see we've got the wide, fast, deep. We extend up to the north to get the north ecliptic spur. So this is for solar system objects. We have 5 or deep drilling fields where we'll go extra deep in the survey, and we very lightly cover the galactic plane in the south celestial pole because these are either high air mass or at high extinction, so we expect to get less signal from those regions, so they're covered a little less densely. So for Rubin Observatory, scheduler is a misnomer that we often use. What we really need is an artificial intelligence to make real-time decisions about what we should attempt to observe. Usually for telescopes, schedulers solve maximization-like problems. So over here is the Kepler Space Telescope. They designed their scheduler and their cadence to maximize the probability of finding a planet in the habitable zone. They really had a single science goal they were maximizing for. Down here is one of the Gemini telescopes, and they have a telescope allocation committee, and so they set their schedule to kind of maximize the happiness of the TAC. We have these 4 broad science goals, and I don't know how many supernovae equals an asteroid, so it's very difficult to cast the Rubin scheduling problem as a maximization problem. Instead, we need something that can dynamically recover from, say, clouds rolling in and start making good decisions on where to point the telescope again, even in the case of interruptions. So what we've decided is that we really have 3 things that we need to balance, and if we give any of these 3 things too much weight, it will ruin the other 2. We want a nice uniform survey footprint. That's for cosmology, so we get a nice even catalog of galaxies across the entire sky. We want our individual images to be as deep as possible, and we want to keep our slew time to a minimum. We don't want to be slewing the telescope all over the sky. We want to be pointed and with the shutter open for as much as possible. So the scheduler we've designed is basically a decision tree, where the first part of the tree is checking for those deep drilling fields. If there's one that's up and needs observing, it does that. But that's only about 10% of our time. Most of the time is spent in this part of the tree right here, where we look and see if we can observe a continuous area of sky for about 44 minutes, and it's not currently twilight. And if it is close to twilight or in twilight, we go down to the 3rd branch and say, just pick the best spot in the sky. And so for these 2, we use a Markov Decision Process to select the best blob or best pointing in the sky. So the Markov Decision Process. Here's a very brief outline of how a Markov Decision Process works. It's built on features that are basically any information about the state of the telescope, the sky, the survey history. We use those features to build basis functions. This is where we capture our domain knowledge and kind of use a lot of astronomer intelligence to build our basis functions. Then it gets a little simpler. Our reward function is just a weighted sum of our basis functions. And finally, once we have that reward function, we pass it to a decision function, which decides what to do. So let me go ahead and simulate a few weeks of Rubin observatories, and I'll pause and show you what our basis functions look like. So our first basis function is the survey footprint. We have the desired survey footprint minus what's actually been observed. So negative areas are parts that have been over-observed. Positive areas are parts of the survey that haven't been observed at all yet. And I've rotated all of these basis functions to be in Alt-As. So zenith is at the center of the image, and the rest of the sky is spread out there. And so you can see there's the wide, fast, deep region, the north ecliptic spur up here, the south celestial pole there. And so those parts haven't been observed yet, but they're not as far behind as some of the unobserved parts of the wide, fast, deep. Our next basis function is the 5 sigma limiting depth in each filter. And so this is computed from the current sky brightness, the current seeing conditions, and the air mass all over the sky. And so here's a map of it. Again, zenith is at the center. And you can see there's a strong bias towards we want to be on the meridian, which is kind of what you'd expect. The moon is not currently up, so it's symmetric, and there's a penalty for going to high air mass, not much penalty for staying on the meridian. And finally, slew time. We have a kinematic model of our telescope, and so we have a large penalty for slewing to the entire other side of the sky, and no penalty for staying right where we're at. We also have a couple mask basis functions. We avoid the zenith because we're an Alt-Az telescope. We can't track through the zenith, and we avoid the moon, so we have a mask around the moon. So we sum all of those together with various weights on each one. Those weights are free parameters, so because we have very few basis functions, this is a low-dimensional space to explore and optimize. And you can see here's what our final reward function looks like. Over here at high air mass, where we've observed a lot already, it's very negative. And over here, where we're at low air mass and haven't observed, we have the maximum. So we can clearly see, this would be a good spot to observe. So this is our final reward function. It goes to our decision function. We have a tessellation of the sky that we randomize every night. And so we'll translate points in the reward function to actual pointings of the telescope. And that's how we're going to dither the telescope and make sure our final survey ends up extra smooth. We get a list of about 35 pointings where we'd like to point and their associated rewards. If we sort those by how much reward there is, how much we want to observe them, we get a messy pattern like this. So we pass that to a traveling salesman problem solver and get a nice smooth distribution like this. So we've, again, tried to minimize our slew time and go as efficiently as possible. And when we get this list, we're going to traverse this path, swap filters, and traverse it again. That way we get pairs of images separated by about 22 minutes. That's so we can detect solar system objects that have moved, and any new transients that have gone off, supernova explosions, and so on. We'll get color information and not just a single filter. So here is one example night of observing with Rubin Observatory. On the top is in RA deck space, on the bottom is in Alt-Az space. So we start over here just taking single images. Then once twilight ends, we move to taking blobs. We'll take a deep drilling field. So here's 96 observations that we just tracked across the sky for about an hour. And then we go back to observing blobs and then back to twilight time. And you can see in Alt-Az space, we're doing a good job staying near the meridian. We're not falling to high air mass, and we're tracking the deep drilling field when it's near its optimal passage. So this seems to be doing a good job. And again, this is what the survey looks like at the end of 10 years, and we do indeed end up with a nice smooth 18,000 square degrees along with our extensions that we've talked about before. So here's what the distribution looks like in Alt-Az, and again, you can see over 10 years we are sticking to the meridian. We avoid the zenith because we have to, but pick things up on either side as quickly as possible. And very, very rarely are we chasing objects to high air mass. Here's what we call the Hourglass Plot, where I'm showing time within the night on the y-axis and different nights along the x-axis. This black line at the bottom is showing the phase of the moon. And so because we have that 5 sigma limiting depth basis function, we're switching to redder filters like Z and Y at full moon, and then our bluer filters, UGR, when it's dark time. So our basis functions are making us intelligently pick which filter to go with. White stripes here are simulated downtime for weather and mechanical issues. Some technical stats about our simulations. It takes about 8 hours on a single core to simulate 10 years of Rubin observations. That generates our 2.2 million observations. We record all the metadata for each one, so the RA deck filter, and then the sky brightness, the seeing, things like that. It's not too tough to install, but sky brightness is actually the big hurdle. So we have 95 gigabytes of pre-computed sky brightnesses. So if you want to run a full 10 years, you need those. And we've adopted the code is the config. So this is object-oriented, so you have to write about 300 lines of Python to build up this decision tree and these Markov decision processes. And the code is on GitHub, if anyone wants to try it. We've been running on the Hyatt cluster at University of Washington. So now that we have kind of a baseline scheduler that behaves well and doesn't go off the rails, we can start doing experiments. And so here's an example on the left. I've got upper left here is a 10-year baseline survey, and on the right is an experiment where we change the footprint slightly to avoid high dust extinction regions, and we also introduce what we call rolling. So if we look down here, year 3.5 to 4.5, the baseline looks pretty much the same. It's very smooth, but in rolling, we select declination stripes where we emphasize observations for that year. So instead of getting just around 80 observations per year, we can get 140 observations per year. So for half the sky, we'll get very well sampled light curves, and then the next year we'll switch so that in the end, we still end up with a very smooth final survey. We've developed a system for looking at the science performance of our simulated surveys. So here's an example looking at the number of galaxies we would expect to find across the sky for a given survey. And again, dust extinction really hurts for the galaxies. But then we also can take a model of the Milky Way and look at how many stars we expect to recover across the entire survey. And now the opposite, where the folks who want to study stars definitely want to look at the galactic anti-center, whereas galaxies, they want to avoid the anti-galactic center. So we see the scientific trade-offs that we have with different survey strategies. And then here's an example where we use a Monte Carlo to generate 10,000 microlensing events to see which microlensing events could be recovered for a simulated survey. You can see the bulge jumps out as well as the large and small Magellanic clouds, because that's where we expect most of the microlensing events to be. And so we can say how well we're doing. So here's an example. We're working with the scientific community to build up a suite of science metrics so we can look at these trade-offs. And here's kind of an example plot where our most recent release of simulations and how different science cases do depending on that. And the great thing about working from home and during COVID is my kid keeps coming in and showing me different Pokemon and their stats, and I realized, wow, that's a great way to visualize it. So if anyone wants to know how to make a plot like this, just look up Pokemon radar plot, and there are lots of great examples of how to do those. So in conclusion, we have an artificial intelligence that is a decision tree plus a Markov decision process, and it can schedule the Rubin Observatory pretty well. We've released over 200 simulated surveys so far based on some Cadence white papers that we solicited. And the survey strategy is still in active development. So full survey operations won't start until 2023, but obviously in these trying times, that is subject to change. And so I would invite anyone who is interested in the scheduler conversation to come join us. We have a message board at community.lsst.org. So if you have ideas on how we should run our survey, where we should point, or if you have a science case and want to make sure we are incorporating your science and getting the most out of the science, we can help you develop those metrics as well. Thanks a lot.